All right, welcome to the Ideal Qualitative Study with a Quantitative Component 6-week webinar class. William Bannon here again, bringing you the presentation of StatsWhisper. So where are we in our webinar agenda? We are at week 5 already. So this week, we're going to talk about a very engaging topic, statistical analysis with small samples. Now this makes complete sense since we're talking about mixed methods and qualitative analysis, which usually uses rather small samples. This will be very useful for us. So we will examine which statistical tests we can apply when we have a small sample size. So now recall, way back in week 1, we mentioned what parametric and non-parametric statistical tests are, right? So there are 2 broad classifications of statistical procedures, right? So parametric tests involve test assumptions, right, that are often difficult to satisfy when you have a small sample size, right? So in these instances, non-parametric tests are commonly seen as alternatives to use in statistical analysis. Right? So specifically, parametric tests are based on assumptions regarding the underlying population from where the data are drawn. Right? So to put that in practical terms, right, for example, parametric tests assume that within a population, scores, right, continuous scores, are normally distributed. So within our sample, we would need to have our continuous variables have normally distributed scores so it reflects what is assumed to exist within the population, right? So age, for example, right? So our first example here, age. Age in the population has a normal distribution of scores, right? So within our sample, there should also be a normal distribution of age scores, right, to match. So you could imagine if you have a small sample, say less than 30 people, right, it's hard to get a representative, continuous range of scores for age per se, right? So it's hard to find 25 people that represent the entire, continuum of age scores in the population, right? So it's hard to get that, if you have a small sample, to get it to look like, the full population, right, which may violate the test assumption, right? So let's not take my word for it, right? Let's actually put this into practice and see for ourselves, what we're discussing. So let's compare the normality of the full 100 residents we have, right? So we have 100 residents in the full analysis, and their scores are normally distributed, reflecting the population. Now let's take 25 residents from there and see if among those 25 residents, if they do not reflect the population as well as a full 100, right? Now, important thing to keep in mind, we're looking at the test assumption of normality, right, which is fine, but it's our example. So there's other test assumptions that need to be examined. So it's not like you could just look at normality, and if that's fine, then all the test assumptions are met. There's a bunch of them, right? But we're just going to take normality and use that as an example. So first, let's look at the factors that impact normality. All right, here we go. So this is our classic bell-shaped distribution, right? So it's a distribution of continuous scores, right? Not categorical, continuous, right? So it's our distribution of continuous scores. Now, so the shape is important. You got the semicircle looking bell curve, right? So the shape's important. You see in the center, the 0, that's the mean score for whatever variable you're looking at. And the negative 1 through 4 to the left and the positive 1 through 4 to the right reflect the number of standard deviations from the mean, right? So how far the scores are dispersed from the mean score. So the middle, right, the mean, the most alike scores. And as you go to the tails, to the right are the significantly higher than the mean scores, and to the left are significantly lower to the mean scores. Now let's illustrate this. Right? So what's a normal distribution look like, right, using one of our variables? Now, as I said, recall, right in the center, within that one standard deviation, right, the -1 to +1, if you look up the dotted lines, that's 68% of the cases. So that's telling us 68%, or roughly 2/3 of all scores in the population, whether it's age, depression, happiness, whatever it is, about 2/3 are going to be within one standard deviation of the mean, right? So if we look at class attendance, right, so check this out. So we're going to apply actual data to this bell curve to make it more real, right? So we reach out and touch it, right, so we can see how those scores are distributed among the bell curve. So to the left, right, way to the left in the tail, you have 0, right? So that's the possible range of scores for class attendance, which we're looking at. So 0 is the lowest, so that's where the left-hand side begins. Now all the way to the right on the other side is the highest possible score of 7. So they can attend class from 0 to 7 days per week, right, on average. And that's what that reflects, the extremes, the extreme of 0, never going at all, to 7, going to class every single day. Now right in the center, we have our mean, right, our 3.69. That's the mean score for class attendance. So the average resident went to class almost 4 days a week, right? 3.69, more like 3 and 2/3, and the standard deviation is 1.81. So if we add 1.81, one standard deviation, to 3.69, right, you see we get 5.50. And if we subtract 1.81 from 3.69, we get 1.88. So that's one standard deviation above and below the mean. So we would say that 68% of residents attend class between 1.88 and 5.5 days per week, right? So that's how that distribution falls out. And then, of course, if 68% are in the center, then 16%, are outside the mean on either side. So if you go to the left of the mean, the left of, one standard deviation below the mean, right, 16%, so these are the significantly lower ones, go to class 0 to less than 1.88. And to the right of one standard deviation of the mean, 16% of residents go to class above 5.5 to 7 days per week. So that's the normal distribution, right? So that's what we want to see. But it's hard to get this, right, with only 25 people per se rather than 100. Now, let's look at things that impact the normal distribution, okay? So you have the skewness and the kurtosis. Skewness is the peak. Kurtosis are how cases are distributed along the continuum to the tails. Right, so bad kurtosis could be when the peak favor to the left or the right. And good kurtosis, normal distribution, is represented here in A, where there's a good peak and the tails are rather full. B is bad kurtosis because there's no peak and the cases are instead in the tails. And C is bad kurtosis because there's too few cases in the tails and they're favoring the peak, right? So kurtosis and skewness is how we reflect if our distribution is normal approximately. So one of the ways to tell, right, so how do we assess if there's normality within this distribution, right? So one of the ways to tell is if the skewness is within 3 times the standard error of the skewness, right? If it's 3 times or below, it's approximately normal. And the same with kurtosis. Is the value of kurtosis within 3 times the standard error of kurtosis, right? If yes, the cases are approximately normally distributed within the variable. So here are the directions, right, for figuring out kurtosis and skewness in SPSS. Right, so this is the same as our frequencies, but if we wanted to go do that, you know, you just go to Analyze, Descriptives, Frequencies, right? And then, for example, we might put class enjoyment over here. And then when you go to statistics, you would just click dismiss and kurtosis, right? And OK, or continue, then OK or paste, right? And there's that. But we have it in our slide. All right. So, and there's the actual instructions. So there we go. So that's what comes out for our full 100 residents, right? The skewness and kurtosis. For example, you can see age. The skewness is, you know, negative. The negative doesn't matter, but 0.35, and the standard error is 0.24. Now, if you divide one by the other, you'll get a ratio of the skewness to the standard error, and the same with the kurtosis and so on. So this is what that would look like, right? So if we divide the skewness by the standard error of the skewness and the kurtosis by the standard error of the kurtosis, for each variable, we get a ratio saying, you know, how many more times bigger is the skewness or kurtosis relative to the respective standard error. And you could see none of the ratios are above 3, right? Which means among all the variables, none of them have a skewness or kurtosis that's 3 times the respective standard error, right? So for the full sample of 100, the distributions are approximately normal, right? So the test assumptions are not violated. Now here's where it gets very interesting, right? So we have 25 residents, right? 25 of the 100 residents. And we also computed the skewness and the skewness and kurtosis and standard error of each for them. So what we're going to do now is the same thing, where we divide the skewness and kurtosis by the standard error of each. And you could see that 2 of the ratios are high above 3, right? So in terms of class enjoyment, right, the ratio is now 4.78, so significantly non-normal skew. And regarding the kurtosis, the ratio is 4. So a significantly non-normal skew and kurtosis, right? So therefore, the assumption of a normal distribution is not met when we switch from the sample of 100 to a smaller sample of 25, right? So that's the point. Now, how bad is it that the assumption is violated, right? What are the implications? That's something we will discuss. So, first of all, the whole reason we're discussing this is that incorrect results and conclusions result when data deviate strongly from the assumptions of the parametric tests, right? So at times, like when the distribution is non-normal, like we just saw, you need an alternative, right? An alternative way of testing, and that's where the non-parametric tests come in, right? So what you should do, and what we'll do, is consider not only the parametric test, but also the non-parametric equivalents to address this problem of not meeting those test assumptions, right? So the thing is whenever there's a problem, there's also a solution. You just got to know what the solution is, right? Which is what we're talking about today. So even with statistics, there's no dead ends. There's problems, there's solutions, there's discussions. All right, so the non-parametric tests are not based on as many assumptions as the parametric, as we've said. Right? So there's no assumption about the distribution of scores in the population. Right? So if there's a violation of test assumptions, we can consider the analogous parametric procedure. Now, here's what we need to keep in mind, and this is a very, very important point. Right? The parametric tests are not, repeat, not, an absolute and complete substitute for the parametric tests. Right? So they can't do everything that the parametric test can do. Right? For example, limitations, right? So see the title, limitations of the non-parametric tests. Okay? So non-parametric tests generally have less statistical power relative to parametric tests, even when you're using the same sample size. So if you have 25 people in your sample and you apply parametric and non-parametric tests, the parametric generally have more statistical power to detect a significant relationship. Right? So therefore, analysis is likely to show a significant relationship, right, using the parametric tests. If we take an example, let's say class enjoyment is related to the dependent variable class attendance. If the effect size is small or medium, right, with the same number of people, the parametric test may pick it up, where the non-parametric test may not see that relationship. So that's one limitation. Here's a big one, and we're going to address this too. But this is a big one, right? So the non-parametric tests are limited in describing variable relationships, right? Specifically, non-parametric tests have the equivalence of bivariate analysis from the parametric test. So that is to say, if we do a statistical analysis using non-parametric tests, we're essentially doing the equivalent of the bivariate analysis from the parametric test, the t-test, the ANOVAs, right? There's no multivariate non-parametric test, right? So there's not a non-parametric multiple linear regression in the SPSS program we're using, right? So what are the implications of that? That means we can't examine the relative strength of each predictor in describing the dependent variable. So recall, the multivariate test told us, right? So we put several variables in the regression, and the multivariate test, the regression, told us which was the strongest predictor, right? We don't have that in the non-parametric testing. So we can't see the strongest predictor among all the predictors. We can only see what bivariate analysis told us, which is what's related to the dependent variable one-on-one, right? But we can't see which is the strongest predictor, right? So that's a big limitation, especially in our study. All right, so many times as a solution, it's worth conducting both, right? The bivariate parametric and the bivariate non-parametric, and then moving into parametric testing at the multivariate level, right? So it's worth doing both, and that's what we're going to do, right? In essence, the parametric tests, the non-parametric tests, pardon me, become like a complement to the parametric tests, right? And they help validate the methods and findings. So one thing to keep in mind, right, is just because you have a small sample, it doesn't mean you can only use non-parametric testing, right? You could use parametric testing, but it has to be done carefully, right? And you have to view all the assumptions and, you know, and as a matter of fact, specifically, right? the tests are robust, right? So that's one thing we need to discuss regarding the parametric tests. Well, I guess the test. Now you may say to me, you understand how coffee is robust, right? But what does it mean when statistical tests are robust? Right? Now this is a real important concept, and it's really going to help us in bridging these parametric and non-parametric tests. So robustness suggests that within a parametric test, if a violation such as normality, a normal distribution, if an assumption, pardon me, is violated, such as a normal distribution, right, that you'll still get the same results, right? The results are dependable even if the assumption is violated. That's called being robust, right? That's the robustness of a parametric test, okay? So the reason we could say that is our little tagline down at the bottom here. So findings are similar, right? So in terms of statistical significance, so the same statistically significant relationships are evident, right? Produced within the parametric and non-parametric versions, right? So that's to say, even though the assumption's violated in the parametric version, right, the non-parametric version, where the assumption doesn't apply, is also producing the same findings, right? So that bolsters our confidence, right, that the parametric test is robust. Right, so as we said, that's why we're going to consider using non-parametric tests as a complement to our parametric testing. Right, so even though our sample is small, like 25, we're not confined to just parametric tests. The combination is going to make the analysis fuller and more descriptive. And perhaps most importantly, it's going to provide an answer to our research question. Now, the interesting thing to ponder here is, will it provide the same answer to our research question? Now, in these sort of analysis, right, we're not saying that 25 residents perhaps are representative of all the residents of retirement communities in the country, right? So often these findings are called preliminary. That's the magic word, preliminary. In Brooklyn, they would call them, I'm not saying, I'm just saying, right? So what does that mean? That means we're not saying that the findings are true, the findings within our study are true amongst the entire population, nor are we saying that, because of the findings among 25 residents, that practice and policy decisions should be changed, or guided by our findings. What we are saying is that these valuable findings indicated, X, Y, Z. Thus, they may warrant further study, right? And that's really important and valuable, right? So we know, right, the value of our findings and the limitation of our findings. The value is what's suggested. The limitations might be, it might not be representative, or worthy of basing practice or policy decisions, but it has value, certainly. All right, now for this presentation, this is an important table. This table lists the analogous or equivalent non-parametric tests for every parametric test. Okay, we're going to apply this to our data between the full sample and the partial sample. So let's put ourselves in the shoes of the analysis with 25 people. Okay. So assume we have not yet done any quantitative or qualitative analysis. So we don't know what the variables are. We don't know what the findings are, on the quantitative or qualitative side. Okay, so that's where we are right now. We're just going to take data from 25 residents and analyze it. Right, so from the administrator's list of 100 residents, we take every fifth and then the last 5. Now, if you look in the SPSS database at the variable ID, you'll see every fifth resident has been selected, right? And then the last 5. So that's where we have our 25 cases for analysis. And so the result is we have 25 community residents to participate in our mixed methods analysis to answer our research questions and our hypothesis. And again, will this analysis produce the same findings as the larger study, right? Specifically, right? So we know the larger study, 100, that's sort of our entire population because that's what they wanted to examine, the administrators. So we had the resources and time to collect data from all 100. So we actually know the metrics for the population per se, the whole 100 people. So however much the findings deviate from what we had with the full 100 using the 25, right? We know the findings are missing something, okay? So what we want to know is how close are the findings, right, with the 25 residents relative to the findings with the full 100. See, that's what's so interesting about this analysis. We know the actual relationships that exist. So now with this smaller sample, we want to see if those relationships are evident using a smaller sample, okay? So we could also ask at the bottom, could we have just involved 25 residents in this mixed method study? Right? So that makes sense because mixed methods and qualitative analysis, 25 sounds like a good number to have. That's actually a pretty solid number, right? So we want to know if we only did the analysis with those 25, would we have gotten the same qualitative and quantitative data and findings? So univariate analysis. So I went ahead and did this. We did this in week 2 of the univariate analysis process. And we have here our continuous variables. Now let's compare them. Right? So on the top part, see above the line, n equals 100. Those are the values for the full 100. And then n equals 25 on the bottom. Those are the values for just the 25 residents out of 100 we're using for this analysis. Now, if you look at class attendance, you'll see for the full 100, the mean is 3.69, right? And the min-max is 0 to 7. So the average resident, went to class 3.69 days per week, right? Almost 4. And among the whole sample, there was people that didn't go to class at all, 0, and some that went every day, 7. Now, when we look at the 25, right, below it, class attendance, the mean's a little lower. It's 3 times a week, so the average of the 25, the average resident went to class 3 days per week. And there was nobody that went to class 7 days per week. It's 0 to 6. So among the 25, the highest one only went to class 6 days per week. Then we look at age. Age at the top, 79.29, and then the bottom for the 25, 84.28. So the age is a little higher for the 25. But the real story is class enjoyment here. So you'll see for the full 100, class enjoyment was 3. The mean score was 3. So the scale is 1 to 5, so 3 is the midpoint. So the average person enjoyed class right at the middle part of the scale. Not really high, not really low, right? But if you look at the 25, the mean of class enjoyment is 1.57. So that's like half the mean of the full 100. So that's a lot closer to the beginning of the continuum so didn't enjoy class at all. It was 1. So the average person for class enjoyment is pretty low. So it looks like if we only use the 25, it looks like people didn't enjoy class that much, when really among the full 100, it wasn't that bad. So then if we look at the categorical variables, right, let's compare those. So doctor prescription of classes, that's pretty close, right? It looks like about, approximately half, right, 40% or so on the top, were not prescribed classes, right? And then 30% for recommended and yes, and it's not that far off, for the 25. And then class assignment, right? So right, it's not too bad. It's about half and half, right? So for the full 100, it's half morning, half evening, and for the 25, 56% morning, 44% evening. So that's pretty accurate too, right? Other categorical variables, right? Same thing for class instructor. So about half and half for both, for Ms. Gentley and Ms. Albright. Now the attendance is a little off because for the full 100, only about a third were not going 3 days a week or more. But for the 25, it's almost half we're not going 3 days a week or more. Right? So what are you going to do? So it's not terribly disparate. So now let's apply these analogous non-parametric tests.